Combinatorics, Lecture 5, Catalan numbers. Let us start from the following grid walk problem. Consider the following grid. So we have a rectangular grid where the southwest corner is called A and the northeast corner is called B, and we have 4 horizontal steps available and 3 vertical steps available. So this is 4 times 3 grid. The question is, what is the number of shortest passes from A to B on this grid? And we assume that all segments of the grid have lengths 1. Solution. In order to go from A to B on this grid, we need to make 4 steps to the right and 3 steps up. And out of these 7 steps in total, the 3 steps up can be chosen arbitrarily out of the 7 steps. Therefore, we need to make a choice of 3 elements out of 7, so the answer to this problem is 7 choose 3. So the answer is the binomial coefficient 7 choose 3. A more general variation is when we have a similar grid which now has m horizontal steps and k vertical steps. And again, so we have the southwest corner called A and the northeast corner called B. Then, if we want to go from A to B in the shortest possible way, we need to make m steps to the right and k steps up. And out of these m plus k steps, the steps up can be chosen arbitrarily. Which of these steps will be steps up? So there are exactly m plus k choose k shortest passes from A to B on this grid. And we can similarly write the same answer as m plus k choose m, because we are also allowed to choose m steps to the right out of our in total m plus k steps. Now let's formulate a little bit more complicated problem. Let us fix a non-negative integer k and consider the square grid where we have the sizes are k times k. So we have k steps to the right available and k steps up. And the rest is similar as on the previous slide. But now we formulate the following question. How many shortest passes from A to B never go above the diagonal which connects A and B? Let us list all cases for small values of k. So we will denote the answer for a fixed k by c sub k, and this number c sub k is called the case Catalan number, and later on in the lecture we will have an explicit formula for this number. So if k is equal to 0, our grid consists just of one point, and in particular a is equal to b, so we have only one pass, and that's a trivial pass, we stay at a. So c0 is equal to 1. If k is equal to 1, our grid looks as follows. So we have just a small square. Here is A, here is B. We can make one step to the right and one step up. And if we want to stay below the diagonal, we must make the first step to the right and then the second step up. So there is only one pass which satisfies our condition. So C1 is also equal to 1. For k is equal to 2, here is our grid. So now it's 2 times 2 square. And now if we want to go from A to B and stay below the diagonal, there are 2 possible ways to do this. We can do 2 steps to the right and then 2 steps up, or we can go right up, right up. So there are 2 possible paths of this form, so C2 is equal to 2. And finally, let us look at the situation where the grid is 3 times 3. So we have 3 steps to the right available and 3 steps up. That's our grid. And now if we look at all possible paths, we will see that there are 5 different paths. So we can go right, 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 up, up, up. Or we can go right, right, up, right, up, up. Or we can go right, right, up, up, right, up. So it's allowed to go to the diagonal, it's not allowed to cross the diagonal and go strictly above the diagonal. Then we can also go right, up, right, right, up, up. And finally, we can go right, up, right, up, right, up. And these are all possible options which we have. So therefore, the third Catalan number C sub 3 is equal to 5. Now we present the general formula for Catalan numbers. That's the main result for today's lecture. Theorem: the Catalan number C sub k equals the difference between two binomial coefficients. The first one is 2k choose k, and then from this one we subtract the binomial coefficient 2k choose k plus 1. If we accept this formula, there is a little bit more compact way to write a formula for C sub k. So C sub k also equals 1 divided by k plus 1 times 2k choose k. So here is a proof. We prove the corollary using the theorem. So 2k choose k minus 2k choose k plus 1 equals, we now use our usual formula for binomial coefficients, 2k factorial divided by k factorial squared, that's the binomial coefficient 2k choose k, minus 2k factorial divided by k plus 1 factorial, k minus 1 factorial. So in order to subtract the two fractions, we reduce them to the common denominator, and to reduce them to the common denominator, we move k plus 1 out of the fraction in the denominator for the second summand, and we multiply both the numerator and denominator with k. So we obtain the following expression. So the first summand is the same, 2k factorial divided by k factorial squared, minus k divided by k plus 1 times 2k factorial divided by k factorial squared. And this, of course, simplifies to 1 divided by k plus 1 times the binomial coefficient 2k choose k. So this proves our corollary. We will start proving our theorem from the next slide, but here let us finish with a small table of the values of C sub k for small k. So if k is 0, then C sub 0 is 1. So C sub 1 is 1, C2 is 2, C3 is 5. We explicitly computed this. C4 is 14, C5 is 42, C6 is 132, and C7 is 429. Now let us describe our strategy to prove our theorem. We will prove a theorem using an explicit bijection, so we will use the rule of bijection. So let us consider the problem of grid walks from a southwest corner to a northeast corner on a k times k grid. So by definition, C sub k is the number of passes here that never go above the diagonal. We know that the total number of paths is 2k choose k. So to prove our theorem, we just need to show that the number of passes that definitely go above the diagonal equals 2k choose k plus 1. And for this, we will establish a bijection between these passes which go above the diagonal and grid walks on a grid of size k minus 1 times k plus 1. So just to simplify our terminology, by a pass on a rectangular grid, we mean the shortest pass from the southwest corner to a northeast corner. And we will prove the lemma as promised, that there is a bijection between the passes on a k times k rectangular grid that go above the diagonal and passes on a k minus 1 times k plus 1 rectangular grid. And to prove the lemma, we will construct an explicit bijection between these two sets of paths. So given a path on a k times k rectangular grid that goes above the diagonal, let us look at the first step, that will be the step up necessarily, that lands strictly above the diagonal. And the end point of this step, let's call it the critical point. So what we do is that after this step, we swap all the remaining steps. So we replace each step up by the step to the right, and each step to the right by the step up. So the critical point appears one step above the diagonal. So until this point, the number of steps up is one more than the number of steps to the right. So after this point, in the normal case, the number of steps up is 1 less than the number of steps to the right. But we swap them, so we replace each step up by step to the right and vice versa. So what we will get is that the total number of steps up becomes 2 plus the total number of steps to the right. And this means exactly that we get a grid walk on a k-1 times k+1 grid. So here's an explicit example. So let's look at our 3 times 3 grid and the walk right, up, up, right, right, up. So the first step, which goes above the diagonal, so we go right up, we are on the diagonal, and then going up, we go above the diagonal. So the end point here is our critical point. After the critical point, we do right, right, up. So now we replace it and do up, up, right. So we get a walk right, up, up. We are on the critical point, and we do up, up, right. And as you see, we are at the situation when we land at the point, which is k-1 times k+1. That's the northeast corner of a k-1 times k+1 grid. Conversely, if we have a path on a k-1 times k+1 grid, the end point of that path is definitely above the diagonal, so the path must contain a critical point in the previous sense. So the first point which appears after we cross diagonal and go up. Again, we take that critical point, and after that critical point, we swap all the remaining steps. We replace up by a step to the right, and we replace a step to the right by an up. And this will output a grid path on a k times k grid that goes above the diagonal because the critical point remains. And the two procedures are clearly inverse to each other, so by the rule of bijection, we get our lemma. And our theorem, of course, follows directly from the lemma. And this completes the proof of our enumeration of Catalan numbers. Let's describe various other combinatorial problems where the answer is given by Catalan numbers. And the first one is the enumeration of light 0-1 sequences. For a non-negative integer k, let us denote by L sub k the set of all 0-1 sequences with k0s and k1s, which satisfy the following condition. Each prefix, and prefixes always starts on the left, each prefix of the sequence contains at least as many zeros as ones. So for example, L3 consists of 0, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, and 0, 1, 0, 1, 0, 1. So we claim that the cardinality of the set Lk is exactly the case Catalan number Ck. Indeed, let us construct a bijection between the elements of Lk and the set of grid walks on the k times k grid that stay below the diagonal. So given a sequence a1, a2, and so on, a to k in Lk, so that's a 0-1 sequence, which is light in the sense that each prefix contains at least as many zeros as ones. So we read the sequence left to right and interpret each zero as a step to the right and each one as a step up. Then the fact that we have k0s and k1s means exactly that this is a walk from the southwest corner of a k times k grid to the northeast corner of the k times k grid. And the condition that each prefix contains at least as many zeros as ones means exactly that this walk stays weakly below the diagonal. And therefore we indeed have a bijection between our 0-1 sequences and the grid walks, and we get the answers that our light 0-1 sequences are enumerated by Catalan numbers. Here is another classical appearance of Catalan numbers, and that's in non-associative products. We are used to the fact that when we compute the sum or product of m numbers, the outcome doesn't depend on the order in which we add or multiply these numbers. And this is due to the fact that the addition and the multiplication of numbers, that they are associative. So a plus the sum of b and c equals the sum of a and b plus c for any numbers a, b, and c. And similarly for multiplication. Now let us ask the following question. Assume that we have some set x and a binary operation star on x. And assume that this operation is quite arbitrary, so in particular not necessarily associative. Now, given m elements in our set, a1, a2, and so on, am, in how many different ways we can compute the product of these m elements? So a1, star a2, star and so on, star am. This is not well defined. If the operation is not associative, we need to specify in which order we multiply these elements. So we need to put brackets. We say we multiply this first, and then next that, and so on. So for example, if m is equal to 3, there are exactly two different ways to multiply a1, a2, and a3. We can multiply first a2 and a3, and then multiply the outcome with a1. Or we can multiply a1 and a2, and then multiply the outcome with a3. And associativity is exactly the property that the two things coincide. And if our star is not associative, there is no reason for them to coincide. If m is equal to 4, then we have 5 different expressions. Namely, if we want to multiply a1, a2, a3, and a4, we can first multiply a3 and a4, then multiply the outcome with a2, and then multiply the outcome with a1. Or we multiply a1 and a2, then multiply the outcome with a3, and then with a4. Or we first multiply a2 and a3, then multiply the outcome with a1, and then with a4. Or a2, a3, then a4, then a1. Or we multiply a1 and a2, separately a3 and a4, and then multiply them together. So as we see, for m is equal to 3 we have 2 things, for m is equal to 4 we have 5 things. That's exactly 2 numbers appearing in the Catalan sequence. So the claim, there are exactly c sub k different ways to bracket the expression a1 star a2 and so on star a k plus 1. Indeed, let us construct a bijection between bracketings of such an expression and 0,1 sequences in LK, so light 0,1 sequences. So when bracketing an expression of k plus 1 elements, we need to specify k pairs of brackets, which start with the left bracket and end with the right bracket. And then we read this left to right, and we record each left bracket as a 0, and each right bracket as a 1. And this clearly produces a unique element of L sub k. Conversely, each element of L sub k defines a bracketing of this expression by interpreting each 0 as a left bracket and each 1 as a right bracket. For example, if we first multiply a3 and a4, then a2 and then a1, then this bracketing corresponds to 0, 0, 0, 1, 1, 1. Another example, if we first multiply a1 and a2, then a3 and a4, and then multiply them together, then this bracketing gives us 0, 0, 1, 0, 1, 1. Here is yet another appearance of Catalan numbers, now in elementary geometry. So let m be a positive integer, which is greater than or equal to 3. Consider a convex m-gon, and then for simplicity one can imagine that that's a regular m-gon which is inscribed in a circle. Let us look at all different ways to split this m-gon into triangles, or triangulate it, by connecting its vertices, and a line connecting two vertices of an m-gon is usually called a diagonal, or a side of an m-gon. So by drawing diagonals, we triangulate an m-gon by drawing diagonals, and the condition is that the diagonals are not allowed to intersect, but they can touch at the endpoints. So for example, there are exactly 2 different ways to triangulate a quadrangle. So we have a quadrangle, 1, 2, 3, 4, our vertices, which is inscribed in a circle, and we can draw the diagonal 1, 3, and then it's triangulated, or we can draw the diagonal 2, 4, and then it's triangulated. For a pentagon, so an m-gon with 5 vertices, there are 5 ways. So here is our pentagon, 1, 2, 3, 4, 5, in a circle. The first way is we use diagonals 1, 3 and 1, 4. The second way is 3, 1, 3, 5. Then we can do 4, 2, 4, 1. Then we can do 2, 5, 2, 4. And then we can do 5, 2, 5, 3. These are the 5 different ways. And then we see the sequence 2 and then 5. And then if you look at triangulations of a hexagon, we will see 14 possible triangulations. So we have 6 possible triangulations when we start with one vertex and then draw diagonals to all the opposite vertices. We have 6 such things. We can choose the first vertex in 6 different ways. Then we have 3 triangulations where the diagonals look as a letter Z and we rotate it. And then we have 3 more where the diagonals look as the opposite version of the previous one. And then we have 2 more triangulations where the diagonals form a triangle. So these are the 14 ways. So we have 2, 5, and 14. These are 3 numbers which appear in the Catalan sequence. And so the claim is that there are exactly 6 sub k different triangulations of a k plus 2 gon. So we already saw that C2 gives us a number of triangulations of a quadrangle, C3 is a number of triangulations of a pentagon, and C4 is a number of triangulations of a hexagon. To prove the claim, we construct a bijection between triangulations of a k plus 2 gon and bracketings of A1 star A2 star and so on star A sub k plus 1. For this, we fix the side which connects vertices 1 and k plus 2 of our regular k plus 2 gon, which is inscribed in a circle, and the vertices are numbered in a cyclic way. And then, so we fix the side which connects 1 and k plus 2, and then we associate A1 to the side 1, 2, we associate A2 to the side 2, 3, and so on. If we now look at a diagonal of a triangulation of our k plus 2 gon, then the side m is on the one side of the diagonal. So if we interpret this diagonal as bracketing of the expression on the other side. Here is an example. Look at this triangulation of the hexagon, and let us explain why this corresponds to this bracketing of A1, A2, A3, A4, A5. So our side 1, 6 is here, 1, 2 is A1, 2, 3 is A2, 3, 4 is A3, 4, 5 is A4, and 5, 6 is A5. So the triangle 1, 2, 3 tells us, so the diagonal 1, 3 tells us that we should bracket A1 star A2. The triangle 6, 4, 5, so the diagonal 6, 4, tells us that we should bracket A4 and A5. Now the diagonal 6, 3, the triangle 6, 3, 4, tells us that we should bracket A3 with the outcome of bracketing A4 and A5. And then our side 1, 6, that corresponds to the global bracketing, which is the last step, which is always present. So these are the outmost brackets in our expression. And it is easy to see that this procedure defines a bijection between triangulations of a k plus 2 gon and bracketings of A1 star A2 star and so on star AK plus 1. So our triangulations are indeed enumerated by Catalan numbers. One last appearance of Catalan numbers is by the so-called Dijk paths. So definition: and Dijk path of semilength k is a path in a plane from the origin to the point 2k, 0, where each step of the path is either 1, 1 or 1, -1, and such that the path always stays weakly over the x-axis. So for example, here are the 5 Dijk paths of semilength 3. So we have the path 1, 1, 1, 1, 1, 1, 1 -1, 1 -1, 1 -1, the path 1, 1, 1, 1, 1 minus 1, 1, 1, 1 minus 1, 1 minus 1, and so on. Of course, there is the obvious bijection between the Dike passes of semi-length k and the original grid walks on a k times k grid that weakly stay below the diagonal. One should just rotate and reflect the picture to see the explicit bijection. So in particular, the Dike passes of semi-length k are enumerated by C sub k. Some additional problems and questions at the end. Problem question 1. Determine the number of shortest passes from the southwest corner to the northeast corner on a k times k grid that stay strictly below the diagonal except for the endpoints. Problem question 2. How many Dike paths of semi-length k contain the point k, 0? Problem question 3. 10 people want to purchase one ice cream each. The ice cream costs 50 cents. 5 of these people have a 50-cent coin each, while the other 5 have $1 note each. The seller has no change to start with. In how many different ways can one form a queue out of these 10 people so that the seller will always have the needed change available? Problem question 4. Find a bijective proof for the relation that 4k plus 2 times c sub k equals k plus 2 times c sub k plus 1. And problem question 5. Check with all details the bijection between triangulations of a k plus 2 gon and bracketings of a1 star a2 star and so on star a k plus 1. Thank you very much and see you next time.